Dear students, welcome to this session. In the earlier session, we looked into how a rotating magnetic field is created when stator winding is supplied with a three-phase supply. So, when a three-phase supply given to a three-phase winding creates a rotating magnetic field, that rotating magnetic field rotates with a certain speed. Okay, the speed of the rotating magnetic field is called as a synchronous speed, and it is represented as n suffix s, ns, and it is represented in rpm, rotations per minute. The synchronous speed is the speed with which the rotating magnetic field rotates is called as the synchronous speed. So just to repeat, when a stator winding, three-phase winding is supplied with a three-phase supply, it creates a rotating magnetic field. The speed of that rotating magnetic field is called as a synchronous speed, represented as ns. And how do we write the formula for the synchronous speed? ns is equal to 120 f divided by p, and f is what? F is the supply frequency. We are going to give the three-phase supply to the stator winding. That frequency of that supply is the f, and it is represented in cycles per second or hertz, and p is the number of poles on the induction machine. And you can see, for a given induction motor, f, supply frequency, is constant. We know that in India it is 50 hertz, and for that particular given machine, number of poles is also constant. The poles cannot be changed. So the synchronous speed for a given induction machine, it is a constant, and it is given by 120 f divided by p, and it is represented in terms of a rotations per minute, that is rpm. Next is the important terminology, that is slip of the induction motor. Now what is a slip? I told you when we learned the principle of operation, when stator winding was given with a three-phase supply, it created a rotating magnetic field, and the stator winding, which were initially standstill, starts cutting the magnetic flux. So it induces the EMF inside each of the conductor. Since the rotor winding is a closed path, a current will start flowing in the rotor conductors. Now rotor conductors are carrying a current, and they are placed in a magnetic field. Whenever a current carrying conductor is placed in a magnetic field, it experiences a force. Now the rotor is mounted on a shaft, and the force is experienced by all the conductors which are on the periphery of the periphery of the rotor. That will create a torque, a combined effect of all the torques. The rotor will start rotating. So from standstill, that is from zero speed, it will start rotating. And which direction it will rotate? It will rotate in the same direction where the rotating magnetic field is going. So it will try to catch up the rotating magnetic field. When that is again explained by the Lenz's law, it is trying to oppose the cause which is producing the current inside the conductors, and that cause is the rotating magnetic field. So it will try to rotate in the same direction. And what would be the ideal condition when it completely opposes the cause which is producing it? When its speed becomes same as the rotating magnetic field. When both the speed becomes same, then the conductors will not cut any magnetic flux, current will become zero. But that is not the case. The rotor will always try to catch up with the synchronous speed. It will not be able to catch with that speed. It will always lag by some magnitude, and that is called as a slip. What is a slip? The difference between the synchronous speed of the stator's rotating magnetic field and rotor speed is called as a slip. So what is a slip? Very simple differential, ns minus n. What is ns? Synchronous speed. What is n? N is a rotor speed, and we can represent it in either as a percentage or as a fraction. In case of a percentage, s would be lowercase s, slip is equal to ns minus n divided by ns into 100, that is the percentage slip. And ns is synchronous speed, n is the speed of the rotor, and this is represented in the percentage. Slip can be also represented as ns minus n divided by ns. So what would be the it would be represented in the fraction. Okay, so that fraction value would be always less than 1. So initially you can just we can analyze few things from this formula. Initially when the supply is given to the induction motor, the rotor is standstill. What is the meaning of rotor is standstill? The rotor speed is 0, isn't it? The rotor speed is 0, and what would be the slip at initial start of a machine? Ns minus 0 divided by ns into 100, that is ns divided by ns, that is 1. The slip is 100%, and in terms of a fraction, ns value would be 1. Similarly, when the motor starts picking up the speed, so when it starts picking up the speed, it will become very close to ns. Okay, for example, we will take this as 1000, and if 1000 rpm is the synchronous speed, and let's say the rotor rotates up to 900 rpm, then what would be the slip? 1000 minus 900 divided by 1000, that is 1000 minus 900 is 100. 100 divided by 1000, that is 1 by 10, that is 10%. The slip would reduce. The meaning is, initially when the machine is about to start, the slip value is very high. As machine starts rotating to its full speed, the slip will come down. Next, this is the derivation, important derivation. Rotor current frequency f dash, it is represented as f dash. We talked about whenever there is a three-phase supply given to the stator winding, it creates a magnetic field, and that magnetic field is associated with the rotor conductors, and the rotor conductor experience the change in the magnetic field. EMF is induced. Since the rotor winding is a closed path, rotor current will flow, right? Rotor current will flow, and all these are alternating quantities. The rotor current that is generated inside the rotor conductor is also alternating, but its frequency would be different. It will not be same as the supply frequency. We have to do the derivation for the rotor current frequency, and it is represented as f dash. The frequency of a voltage or a current induced due to relative speed between winding and a magnetic field is given by the formula. We have derived this formula already. Frequency f is equal to np divided by 120. And what is n? N is the relative speed between the magnetic field and the winding. And what is the relative speed between the magnetic field, that is the rotating magnetic field, and the rotor winding? The speed of the rotating magnetic field is ns, and the speed of the this rotor winding, which is n, that is the speed of the rotor. So what is the relative speed? Ns minus n. So this is ns minus n. If you want, you can represent it as n dash. If it is confusing, n dash. So that is how it is represented in the notes. You can refer that. So n is the relative speed, p is the number of poles divided by 120. Now replacing the same equation here, for a rotor speed n, the relative speed between the rotating flux and the rotor is ns minus n. Consequently, the rotor current frequency f dash is given by f dash is equal to ns minus n into p divided by 120. And already we know what is a slip. Slip is given, this is the fractional slip. Fractional slip is s is equal to ns minus n divided by ns. Now if I multiply this equation with ns, okay, and divide it by ns, ns minus n divided by ns becomes the slip into ns into p divided by 120. And from the previous discussion we know what is the ns value. Ns value is given as the synchronous speed. Ns is equal to 120 f divided by p. And what is the f? F is the supply frequency. And how do we get the supply frequency from this equation? F is equal to ns into p divided by 120. That is what we are going to replace here. See, f is equal to ns into p divided by 120. So this ns p divided by 120 is replaced with f. So what is the formula? F dash is equal to sf. What is f dash? Rotor current frequency is equal to slip into the supply frequency. Okay, and very important, this particular slip is represented in fractional format. Ns minus n divided by ns. It should not be multiplied with 100. So you can see that is rotor current frequency is equal to fractional slip into supply frequency. Now when we'll consider some cases as we considered in the slip, when the rotor is at standstill or stationary, when it is about to start, slip is 1. We discussed this earlier. The frequency of when slip is 1, f dash is equal to f, means what? When the motor is about to start, the rotor current frequency is same as the supply frequency. Okay, same as the supply. If supply frequency is 50 hertz, initially rotor current frequency would be 50 hertz because s would be 1 initially. As the rotor picks up the speed, relative speed between the rotating flux and the rotor decreases, consequently slip s, and hence rotor current frequency decreases. So as motor gains the speed, the slip will start reducing. The slip value will start reducing. So is the value of the rotor current frequency. So initially the rotor current frequency is very high. Very high means it is exactly same as the supply frequency. As the motor starts picking up the speed, when it runs to its full speed, the frequency of the rotor current would be minimum.